Hello students, in today's video we are going to work on the mean value theorem, so let's get started. Go ahead and try pausing the screen and try solving this warm-up on your own. So hopefully you've paused the screen and you're just coming back to check your answers now. Now keep in mind it's asking you to find the slope of the line that connects the endpoints of the graph. So this is actually a much easier problem than you would think. All you're essentially doing is you're finding f of 3 minus f of negative 2 and you're dividing that all by 3 minus negative 2. So basically we're using the slope formula here. And what happens is you find that f of 3 is 16 minus negative 29 all divided by 5. And then by simplifying further we get that that's 45 divided by 5, which is obviously 9, and that's going to be your answer. That's the slope of the line. So again, we're working on the mean value theorem. So let's go ahead and define that. So the mean value theorem states that if y is equal to f of x, so if we have a function that's continuous at every point on the closed interval a and b, and it's differentiable at every point of its interior a and b, then there is at least one point c in that interval at which f prime of c is equal to f of b minus f of a all divided by b minus a. So just to clarify, if we have a function that's continuous in a closed interval and it's differentiable at every point in that interior, that means it's not a cusp, vertical tangent, discontinuous, or a corner, then that means it's differentiable. And within that, it means there's a point c that lies within that boundary. That means that we could take the derivative and substitute c in, and that would be equal to the slope of 2 points in that closed boundary. So I know that might not make any sense still, but let's look at a physical interpretation. So what we're saying is that the instantaneous speed, now remember instantaneous speed is the derivative. If we take the derivative of any function and substitute that value in, that gives us the instantaneous speed. So it says that instantaneous speed at some interior point must equal the average speed over the entire interval. So that means if we take the average like we did in example 1, or the warm-up, and we could find some point inside that boundary of negative 2 and 3 that's equal to that slope if we take the derivative. We'll have some more time to play with this in a little bit. It says, here's another thing. It says if a car's average speed for a trip is 30 miles per hour. So if we were driving for multiple hours and that average speed is 30 miles per hour, then that means that the speedometer must have read 30 miles per hour at some point during the trip. So if we average 30, at some point that instantaneous speed must have been 30. So there's a special case of the mean value theorem, which is called Rolle's theorem. It states that if f of a is equal to f of b, and that's equal to 0, then there exists, that's backwards e, then there exists some c that's an element in a and b. That means that there's a c inside of this boundary that exists in this interval, such that f prime of c is equal to 0. So it says that if fa equals fb equals 0, then there is some point in that interval such that that derivative at that point is equal to 0. So what that's getting to is it starts to tell us about critical points, and it starts to tell us about increasing, decreasing values. So I'm going to read this to you quickly, and then we're going to go over some practice. It says, let f be a function defined on an interval I, and let x sub 1 and x sub 2 be any 2 points in that interval I. It says f increases on I if x sub 1 is less than x sub 2. Then that implies that f of x sub 1 is less than f of x sub 2. So that basically means if x sub 2 is a greater value than x sub 1, then it also means that the function with that number plugged in is greater than the value of x sub 1 substituted into the function. Conversely, f decreases on I if x sub 1 is less than x sub 2, then f of x sub 1 is greater than f of x sub 2. So it's basically saying if we take these two values and substitute it in, then that'll help us determine if it's increasing based on these factors. And I know that's a little scarce, but we're going to have lots of problems to work on that and explain it further. Now, a function is called monotonic, mono meaning one, tonic, if it is increasing everywhere inside an interval, or if it is decreasing inside an interval. So it's monotonic if the graph is either increasing or decreasing, because it's only going in one, hence monotonic direction. So here's a little bit more about increasing, decreasing values. It says that f be continuous on AB and differentiable on AB. If f prime is greater than 0 at each point of AB, then f is increasing on that closed interval. If f prime is less than 0 at each point on AB, then f is decreasing on that interval. So let's get to something that's going to make more sense to you. Now if we have this function, y equals x to the fourth minus 10x squared plus 9, we're supposed to find the local extrema and find the local when the intervals are increasing and decreasing. So let's just for a second take a look at this graph. Now it's x to the fourth graph. So if we take a look at a quick graph, it's an x to the fourth graph. That means the end behavior, going back to your pre-calc days, are going to be both going upwards because it's a little bit like a parabolic shape. So at some point this graph could change. It could just look like a U because this fourth root or this fourth power tells us there should be 4 times where it crosses the x-axis. 1, 2, 3, 4. It also tells us that there are 4 different changes from increasing to decreasing. So as we go down, that's all going down. Then it goes up. So that's one increase change, or it's one change in increasing, decreasing. Then it goes down. That's a second, and here's a third. So let's take a look at how that works a little bit more. So first things first, to find the local extrema, find the first derivative. So y prime is equal to 4x cubed minus 20x, and that's equal to, and what we're going to do is we're going to set that equal to 0. So 40x cubed minus 20x equals 0. We're going to factor out a 4x. We get x squared minus 5 equals 0. We get x equals 0. And x is equal to square root 5. X equal to negative square root 5. So those are our three critical points. Okay, so far we found our critical points. We haven't exactly found the local extrema, the max and min yet. So let's look at that carefully. Now we know this is a y to the fourth graph. That means the end behavior is going to go like so. And these critical points tell us when those things change. So we know that from negative infinity to negative square root 5, because that's going to be the first point, that's the first critical point we run into. We know that this graph is decreasing. And then we know from negative square root 5 to positive square root 5, this thing is increasing because it's always alternating. And then from square root 5 to, oh shoot, I forgot the 0. Let's try that again. From negative square root 5 to 0, it's increasing. And then from 0 to positive square root 5, it's decreasing. So it's decreasing, increasing, decreasing, And then we forgot from square root 5 to infinity, it's increasing again. So if you take a look at this graph, we're decreasing until we hit negative square root 5. And then from square root 5 to 0, we're increasing. And then from 0 to square root negative 5, we're decreasing. And then square root of 5 to infinity, we are increasing. So this is what your graph should look like. Now, if we take a look at these values that we've just found here, that also tells us our max and minimum values. So if we look at this, we know from negative infinity to square root negative square root 5, it's decreasing. That means this is our minimum. And then we know that from negative square root 5 to 0, it's increasing. So we know that this is our maximum value. And then we know that from 0 to square root 5, it's decreasing. So this gives us our minimum again. So all of the time this is alternating. You're never going to have a max and then another max. So now we found A, B, and C. So let's try another problem together. We're going to look at y cubed minus 5x squared plus 3x plus 9. Again, consider the end behavior here. The end behavior, because it's an x cubed graph, and it's a positive x cubed graph, that means it's going to go this side here, and it's going to go up and to the right here. And in between, it should change directions 3 times. So it's going to go up, so that's one direction. 2, it's going to go down, and then back up. Now keep in mind, this is a very rough sketch, just to give you an idea of this is what our graph should look like, based on our end behavior. So now we're going to take that derivative. So the derivative here, so y prime turns out to be 3x squared minus 10x plus 3. We're going to set that equal to 0. We're going to factor this. This turns out to be 3x minus 1 times x minus 3 equals 0. And finally, we get x equals 1/3 and x equals 3. These are our two critical points. Now, keep in mind, we kind of have this rough sketch in our head, the one that I sketched out in red. Next thing we're going to do is we are going to find the max and min. Or the increasing, decreasing values. So I know starting at negative infinity, that's always where you want to start. So negative infinity to your first critical point, which is 1/3, we know that this thing is increasing. Then from 1/3 to 3, we know this thing is decreasing. And then we know from 3 to infinity, it's increasing again. So based off of that, let's draw in a more appropriate graph. So we know at 1/3, that's going to be somewhere here. It's increasing up to here. And then to 3, it's going to be decreasing. So we knew somewhere at these points, it's going to go upwards, downwards, and then back up. So we know that our maximum is at x equals 1/3, and our minimum is at x equals 3. So now we found our increasing, decreasing values and our local extrema. So hopefully this is getting easier. If not, let's try another quick problem. Now notice, it's y equals 2x cubed, so it's a positive 2x cubed. Let's see if we can do it without a graph this time. We're going to take the derivative. Y equals 2x cubed plus 3x squared minus 12x minus 7. We're going to take the derivative, so y prime is equal to 6x squared plus 6x minus 12. Now we're going to set that equal to 0, because that's how we find our critical points. We're going to factor out a 6 from the entire thing. And then we're going to go ahead and factor it. So that's 6 times the quantity x plus 2, x minus 1. equals 0, and then our critical points are x equals -2 and x equals 1. So again, knowing what we know that from -infinity to -2, because it's the first critical point, it is increasing. -2 to 1, it is decreasing. And 1 to infinity, it's increasing. Now, because we know these facts, we know that the max is max at x equals -2, and we know the min is at x equals 1. So now we found our local extrema and increasing, decreasing values. So hopefully this is getting much, much simpler for you. Now, the consequences of the mean value theorem. Now, this tells you that if f prime of x is equal to 0 for all x, then there is a constant c such that f of x equals c for all x. So if we have a derivative and that's equal to 0 for all x, then that means there's a constant c such that for any value of x, that value is the same for all x. Okay, notice that c is constant. If we look at the second bullet, it says f prime of x, and if that's equal to g prime of x for all x, then there is a constant c such that f of x equals g of x plus c. So the part that's going to be weird now, because we spent so much time on derivatives, is going into antiderivatives. Now, a function f of x is called an antiderivative of f of x if f prime of x equals f of x. So notice the notation change here. F of x is in capital letters, is an antiderivative of the original function f of x in lowercase if the derivative of that big f of x is equal to the little f of x. Now the process of finding an antiderivative is called an antidifferentiation. So all this time we've been spending time differentiating things, finding the derivative. The antiderivative, or doing antidifferentiation, is a process of going backwards. Now there are infinite number of antiderivatives of any given function that only differ by a constant of c. So let's look at a couple examples. Now it says find all possible functions with f with a given derivative. So they're saying, look, f prime of x is equal to 2. What derivative can I take? What derivative can I take so that it's equal to 2? So we know that f of x is equal to 2x. Now, that's going to be one of the possible derivatives of the function because I know the derivative of 2x is equal to 2. But the only thing is, 2x works, but so does f of 2x plus 1. So does f of 2x plus 3. So does f of 2x plus 4. And so to take care of that, you'll notice that all of these numbers that I'm either adding or subtracting are all functions. So what we do is we do f of x equals 2x plus c. So anytime we have a general idea, we always add a plus c to the end of any antiderivative. So let's try another one. For part B, we had to find the derivative of something that's equal to sine x. So whatever gives us derivative of sine x technically had to have been cosine of x. But remember, the derivative of cosine x is negative sine x. So in order to balance that out, we're going to throw negative in front, because the derivative of negative cosine x is negative sine x. And to take into account the constant, we're going to add a plus c. So you can pretty much just add that plus c anytime. Now, let's take a look at part C. The derivative of this is 1 divided by x minus 1. Hopefully you've realized by now the derivative, or the original, or the antiderivative, is ln x minus 1. Because if we take the derivative of ln of x minus 1, it's 1 divided by x minus 1. And remember, we don't know if there was constant or not, so we're going to go ahead and add a plus c. So those are our antiderivatives. Let's try another one now. So find the function with a given derivative whose graph passes through the point P. So this looks like a difficult problem, but it's really not. So what we're going to do is we're going to go ahead and find the antiderivative here. So for this one, f of x equals, first thing we're going to do is we're going to rewrite this. So 4 times x to the negative 3/4. Now if you'll remember, in order for us to find this derivative, we're essentially just going backwards. So instead of when we would have done this derivative with the power rule, which is to subtract 1 and then subtract 1 to the bottom 2, what we're going to do is we're going to go ahead and add 1. So the way that works is, for just a split second, I'm going to separate that from the 4. Now in order for us to do this here, we're going to go ahead and add 1 to both sides, or add 1. That gives us 1/4. So what we're going to do also is, just to balance this out, we're going to divide this thing. We're going to divide this thing by 1/4 as well. So we divided that by 1/4 as well. But what you'll notice here is when we do that, we need to keep in mind that this needs to balance out. So let's try that. And what happens is, when we divide by this 1/4, it turns out that we can copy dot flip, and we end up with x equals 4 times 4, x to the 1/4 power. So let's test that really quick. Let's take the derivative of this. So f prime of x equals 4. We're going to leave there. And then when we do the power rule here, we're going to bring down that 1/4, x to the 1/4 minus 3/4. And we're left with 4, which was always there, times 1 times x to the negative, oops, this was supposed to be subtracted by 1, x to the negative 3/4. So this is exactly what we started with before we took the derivative. So notice it was just a balancing out of this dividing 4 here when we got this answer here. Again, you'll have plenty of time to practice this and ask lots of questions in class. Oh, I forgot. Now we need to take care of that point. So now that we know what f of x is, I'm going to redo that problem up here. We have capital F of x is equal to 16 x to the 1/4 power. Now, we have to add that plus c, remember, because we're not sure what else it could have in there. Now, it gives us this point, 1, negative 2. So what we do is we substitute that y in, equals 16 times 1 to the 1/4 power plus c. We find that we have negative 2 is equal to 16 plus c, because 1 to the 1/4 power is just 1. And then we get c is equal to negative 18, because we subtracted 16 to both sides. Therefore, our equation, or our function, is going to be f of x equals 16 x to the 1/4 minus 18. And so this is our final answer. Now let's try the last problem. So here, same idea. We're going to find out what's the opposite of each one. So we're going to do this a little slowly, and you'll notice it's in pieces because it's separated by addition and subtraction signs. So what would give us 2x would be x squared. Because if we take x squared and find the derivative, it's 2x. If you want to do it the other way that we did in the last problem, let's start off with 2x, and then we are going to do the opposite of the power rule. So it was 2x to the first power. We're going to add 1 there. And then what we're going to do is we are going to add by what we were left with on the numerator, on our exponent, so 1 plus 1. And the derivative of plus 1, or antiderivative of plus 1 is plus x minus derivative of sine x is cosine x, so this will be sine of x. Final answer would read f of x equals, notice this becomes 2, and therefore we can cancel it out with this 2 and this 2, and we're left with x squared plus x minus sine of x. And keep in mind, if I'm not sure, I could take the derivative of each one and we'll find out it's the same exact thing as our f prime. And then of course plus c. Now we want to find the function. So we're going to substitute the 3 in times 0 squared plus 0 minus sine of 0 plus c. So we get 3 equals 0 plus 0 minus sine of 0, which is 0. So we find out that c is equal to 3. Finally, we have f of x equals x squared plus x minus sine of x plus 3. And that's our final answer. So I hope that helps. You'll have plenty of time to practice in class. And that's all for now. So I'll see you guys next time.